Hi everyone. My name is just checking. Okay. So my name is Olivier Grisel. I'm working at Inria in Paris-Saclay, in Saclay actually. This is a talk that I gave at .ai a couple of months ago. It's just I'm redoing it exactly the same. So hopefully you weren't at .ai. Myself, I'm a software engineer working on scikit-learn, the machine learning library, but today I'm going to talk about neural networks, so stuff that we don't really do well in scikit-learn. The goal is to see how neural net can be used to build recommender systems. So just a recap. The traditional application of recommender system is to start from one product and as an input, the green box here, and to find related products based on behavioral data of the users to upsell more products, to put those three together in the basket, or instead of buying this one, to suggest other related products that might be more suitable for the user. It's not necessarily used for e-commerce. It can also be used to increase the adoption of content platforms like streaming platforms like Spotify, for instance. In that case, the green box is the user profile, so this is the input of the recommender system, the context. And the recommendations are based on past listening habits of myself and other users, and suggest automatically a playlist. And in that case, we don't sell the items. We just want to reduce the user interface friction for the user, to simplify navigation and to increase user retention of the service. And also it's also good for hiding holes in the catalog. Like if you have a search-based user interface, people might search for a specific artist like the Beatles, for instance, and assume that Spotify doesn't have the right. I don't know actually if it's the case or not. If you use a user interface that is based on a recommender system, you will not face this problem, you will hide it. So that makes the platform more, you can make more money and keep your users, basically. And other applications of recommender systems are actually search engines. In that case, if you type Python, if I type Python in Google, the input is not just the keywords that I type here, it's also because I'm logged in, my identity, basically. And I get two recommender system output. The first one is the actual search result, and you see that I don't get the snake, and if you scroll down, there is no snake on the first page. It's only about the Python programming language, because I'm a Python programmer. And the second recommender system is the ads, the personalized ads, and you can also see that it's about the programming language. So Recsys nowadays are everywhere. And they can also be used to sell apps on app stores or to personalize status messages on social medias. So I think it's like we should consider this as a personalization system and not just selling items. So just I want to recap the distinctions between the different kinds of recommender systems. So you have content-based recommender system where you use the actual description of the items and the users. So you could say metadata, for instance. For items, it could be the director of a movie, or for users, it could be the gender, the age, or stuff like that. Or you could use collaborative filtering approach. In that case, you don't use any description of the data, you just use past interactions between users and items. And finally, you have hybrid systems that combine the two kinds of inputs. And let's say that content-based algorithms are better when you don't have any past interactions, because you have a new item or a new user in your platform, and that you have the cold start problem. But once you start to collect more interactions, usually it's more efficient or more accurate to use collaborative filtering. There are also two different kinds of feedback that you can collect. The explicit feedback, where you ask especially the users to give a positive or negative feedback or a rating on the items. Or you can more easily collect just positive feedback or implicit feedback that is usually positive. This is much more easier to collect, and you don't put any cognitive load to the user. It's not annoying to ask for this kind of clicks, because by just using the application, you can collect them. So the traditional way to do collaborative filtering is to do matrix factorization. You just have your feedback matrix, the ratings, for instance, if it's explicit feedback, with the users in rows and items in columns. And in that matrix, you have many zeros, because one specific user has seen only or has given feedback for, let's say, 10 movies or 100 movies out of 10,000, for instance. So we try to build a model that will approximate this sparse matrix by the product of two narrow matrices, one for the user embedding, or the user latent factors, and the other one for the item latent factors. And we work in a d-dimensional space where d is from a couple of tens or 100 dimensions. And by doing the product of those two matrices, we can approximate this guy, and we do that by minimizing. Actually, LaTeX doesn't work here for some reason. But basically, we minimize the square distance between the reconstructed rated ratings and the true ratings that we collected in the. So, how we do that with neural network? As we've seen, we can collect user items, but user item interactions. But we have a problem, and we will use embeddings to solve that problem. So I will introduce what is embeddings. And the problem that we have with neural network is that the core of the data that we collect is just integers identifiers for users and for items. And you can also have timestamps and stuff like that. But the core is those interactions, the relationship between symbols. Those numbers here, they are not quantitative numbers. They are just identifiers. They could be strings. And you cannot put identifiers as an input to a neural net, because you do arithmetic operations on those numbers when you use a neural net. And it's completely meaningless to use those numbers directly. So we have the problem of dealing with symbolic variables. And this is actually a problem that we meet in recommender systems, but we also have the same problem with text tokens when we do natural language processing with a neural net. Or, does it work anymore? Oops, sorry. Any kinds of categorical descriptors will induce the same problem, like tags for describing items or movie genres, director names, visited URLs, skills on a resume, product categories, and so on. So as a notation, we say that we have a symbol S in a vocabulary V. This is the kind of terms that we use for NLP, but we will use them for a recommender system. So the way to represent a symbol, the traditional way to use to represent a symbol in a machine learning system is to do one-hot encoding. We assign for each possible value of the symbol a specific dimension. So if all the words in the English vocabulary, that could be 1 million dimensions, for instance, and we put a 1 for the symbol that we just got in the database, and 0 everywhere else. So this is a very sparse representation and a very large dimensionality. And the meaning of the axis is defined a priori. And what is the problem here is that if you have two different symbols, they have the same distance to any other symbols. Like for instance, the distance between carrot and salad is the same as carrot and pig, or carrot and roof, or whatever. So it's not very intuitive to use that representation. A more natural representation would be to use a lower dimensional space. Sorry for the LaTeX here, it's completely broken. But basically, we want a space that is much lower dimensional, like continuous and dense. And the axis in that space has no meaning a priori. And we will basically learn the parameters of that representation. And the goal is that the distance that is induced by that space, we want it to capture the semantic distance as was presented previously with latent semantic indexing for text, but it's a more general way to do that, and it can be done in a supervised manner. And once you have this lower dimensional space, you can compute distances using the Euclidean norm or the cosine similarity. So what you can consider is that an embedding is basically a linear layer as the input of a neural net. And so it's a shame that this is not working, but the embedding of S basically is equal to the one-hot representation of S, so this is a sparse vector, times a matrix W, which has dimension K by D, where D is the size of the vocabulary, so all the possible symbols, and K is a much smaller symbol. So you can see an embedding layer as just a linear layer that takes the original one representation of the symbol as an input and convert it into that lower dimensional space. And W are the parameters, the trainable parameters of the model. And when we will fit the neural net, we will also train the parameters of that embedding. And you can do that if you use a Keras, for instance, as a neural net toolbox, by just appending in your model definition an embedding layer as the input. And the input data will be a vector of integers, the identifiers, and the output of that layer will be the continuous representation. And then, after that, you can put regular neural network components, like a fully connected layer and so on. So, how to use neural nets to build a recommender system? One way to do it would be to take the user identifier and the item identifier of a specific row in your database, and to compute the dot product between the embeddings of those two inputs, and you try to approximate the true ratings by minimizing square loss like this. And this is actually exactly matrix factorization, the traditional matrix factorization that we do in the past. But once you use the neural net building blocks, you have a lot more freedom. You're not constrained to do matrix factorization anymore. And you can, for instance, instead of doing the dot product, you can concatenate those two embeddings and make those activation go through a fully connected multi-layer perceptron, and then minimize the output of that perceptron and the true rating using a square-2 loss, for instance. And if you do that, you can also concatenate additional metadata and build a hybrid recommender system, which is not possible to do easily with a matrix factorization model. It's also possible to build more complex models. If you want to deal with implicit feedback, in that case you don't have a true outcome, but what you do for each item I and item user I and item J that you have as an interaction in the database, you sample randomly out of all the other items an item number k that we will consider as a negative. You compute the positive interaction between the user and the true item, and the negative interaction between the user and the random item, and you build a loss function that will contrast the two interactions. And you want to make the positive interaction lower than the negative interaction because it's a loss and you want to minimize it, basically. And if you do that, you can train directly the embedding on implicit data. And you also can train MLPs as we did before, if you want, instead of doing a dot product. And this is a way to do implicit feedback in your recommender systems. It's also possible to use more complex architecture. So this is a real architecture that is used by YouTube for recommending videos. In that case, the input is the sequence of watches, of video watches that a specific user has seen in the past. And you take all the embedding vectors for all those videos, and you compute the average, and you have this as a first segment of your input. You do the same for the embedding of all the search tokens that you type in the search engine. And then you can add content-based features, like an embedding of the geographic location of the user, the age of the user. You can do some pre-processing of the numerical features. And then you feed that to a feed-forward multi-layer perceptron. and then predict whether the user will click on that video or not. And you do traditional neural network optimization. And for serving, when you want to make a prediction, you actually don't need to compute the softmax, which can be very expensive. You can just use approximate nearest neighbor search on the last layer of the system before the softmax. So what is very interesting with this approach is that you have a lot more flexibility, and you can embed a lot more, many kinds of input. So we've seen discrete variables with linear embeddings, but you can also embed images and sounds using conv nets, sequences of discrete tokens using recurrent neural nets, or even molecules, for instance, with graph convolutional nets. And it all fits together in the same intellectual framework, let's say. So it's once you grasp this way of working, I think you have a lot more flexibility than with ad hoc systems. So I think I should stop here. I just want to say a couple of comments about ethical considerations of recommender systems. Whenever you build this kind of systems, you should be very careful about a couple of things. First, when you build a recommender system, you're going to amplify user behaviors. And if those user behaviors can be discriminatory or unfair, you might build a system that is amplifying this kind of problems. So for instance, if the current society, you have a gender imbalance for tech jobs, for instance, and you build a system that is recommending ads of jobs and fashion items, the system will learn the existing imbalance in the society and will reproduce it even further. And so we'll hide, for instance, tech jobs to women. So that's not going to help fix that fairness issue. You can also have this kind of problem where if you do that for social media filtering or personalization, you can further amplify the existing filter bubble that exists naturally on social media, where people connect to people who share the same opinion. The system can further amplify this kind of stuff and filter or polarize the opinions of the users and prevent discussions, basically. And finally, when you build a recommender system, people might feel that there is this kind of problem happening in the background, but they have no easy way to check whether or not they are a victim of this kind of problem. So I think it's a very interesting area of research, is how to make it possible to do audits, both if you're a designer of the system or if you're a user or a regulator. How can you do that to make it easier, more transparent, to detect whether or not there is this kind of problem? Okay, I think this is it. Thank you very much for your attention.
Thank you, Olivier, for your talk. So, we already have questions.
Thank you for the talk. I have two questions. The first one, I would like to know if we can train the neural network with the implicit and explicit at the same time or not.
With the what explicitly?
The implicit feedback and explicit feedback at the same time.
So yes, there is nothing that prevents you to have a loss function. For instance, if I take this one, this one. So you have this loss function. You can add another term, which will be fed by another network that comes from the data with the explicit ratings. And when you train on your network, usually you use a stochastic solver, like a stochastic gradient descent. And for efficiently reasons, but also because it tends to generalize better than other optimizers. And when you do this kind of stochastic optimization, you have to build a mini batch of data. And basically, when you build your mini batch, you can mix data that comes from the implicit and explicit feedback at the same time. And you just need to have an additional dummy variable that will mask the part of the loss. For instance, half of your mini batch can be from explicit data and half of it can be from implicit data, and you will just compute the loss and the gradient of the loss with respect to the parameters using the two kinds of feedback. And you can share the parameters of this and maybe the embeddings as well between the two kinds of inputs. It's possible. I'm not sure if it's actually going to benefit your final A/B test, for instance, but you can try it. You have the flexibility to do it if you want.
Okay. And the second question is, you see that there is an imbalance distribution between the implicit feedback and explicit feedback. So in this case, how do you deal with this? How the neural network?
Actually, it's quite natural if you do when you build the mini batch, you can say that you want half explicit and half implicit, and you don't care about you have 10 times more implicit than explicit. You sample at random a bit of explicit and a bit of implicit, and you will do many passes over your full training set. But basically, the explicit, that is the minority data, will get sampled a lot more times than the implicit data. So, but you can rebalance at the moment when you build the mini batch. And I think when you do a neural network, rebalancing at mini batch time is the easiest way to deal with imbalanced problems.
Thanks for the talk. Can we use deep networks for RTB applications or not? Like, is the prediction can the prediction be made like in less than 10 milliseconds, like for real time and online prediction?
Yes. I have no production experience, but just by looking at the model, I think it's possible to do it because this kind of network, usually when you build a recommender system, you will use a couple of fully connected layers here, but they are not that big and they are not deep. It's neural network, but it's not necessarily deep learning. It's just like one or two hidden layers or more, or three maximum or something. Like on the Google example, this is the real stuff that they have in production, and so there is this embedding, which is like I don't know, a couple of tens or 100 dimensions. They are concatenated here, and this one I think is 500 dimensions, and this one 200 dimensions, and this one 64 dimensions, or something like this. And so those dot products here, they are quite cheap to compute. And then they do a nearest neighbor search in an approximate nearest neighbor database. I think this part is more expensive than this. I'm not sure, but probably it's the case. And also building the features, like collecting the identifiers, the history of the user, is likely to be even more expensive. So I think this part is, at prediction time, is not a problem.
Thank you for the talk, Olivier. I have one question about first. Do you have some benchmarks about the performance, the model trained on implicit feedback or explicit one?
Usually, but it really depends on what you want to do. The final stuff that you want to maximize is not the accuracy of the ratings. It's just a proxy to making good recommendations. And so the final performance is going to be assessed using A/B testing or something like this. And I think it really depends on the user interface that you give to the users, because if you change the user interface, that will change the statistical distribution of the feedback you collect, and that has potentially a large impact, and it really depends on the applications. But in practice, collecting explicit feedback is a lot more, it's very expensive. Like, many users don't want to rate stuff because it's just annoying, and maybe the users that are rating stuff are not representative of all the other users. So you might have a bias in the explicit feedback that is really harmful. So maybe using the implicit feedback is better. I don't know.
Okay. Next question. imagine you want to make some like multi-arms bandit algorithm in the same framework. What is the best way to plug into the system?
Multi what?
I mean, if you want to add some smart randomization in your system,
Do you have an example? Because
I mean, you want to have some Bayesian approach,
okay.
and you want to I mean.
Okay, so for instance, to
Otherwise
estimate
you-
certain.
Yes, yes. I mean,
So basically,
to deal with exploit problem in this context
okay.
as usual in the recommendation system.
So if you want to give to get some uncertainty on the predictions, naturally on your net when you train it using a logistic loss maximum likelihood for classification problems like whether or not the user will click on the link or not, you naturally have some estimation of the bias or confidence level that is directly approximately calibrated. So you could use that as a measure of uncertainty. I think in the case of Google, what they want to optimize is the expected time the user will play the next video. So they basically multiply this probability here times the length of the video, and they directly optimize something that is very close to their business metric. And the probability is like very natural to interpret in that case. But the kind of uncertainty that you get here maybe is not the best representation. I know for neural nets that you can get some kind of approximate posterior distribution by, for instance, if you use dropout at training time, you can also apply dropout at test time and do many predictions with different dropout masks, and you see the stability of the distribution of the prediction. It's not the true posterior distribution, but it gives you an estimate of the variance, and there are many other ways to do that, but I'm not familiar with them.
Yeah, thank you.
Hi, thanks for the talk. Quick question about the embedding matrix. You said you would optimize it as model parameters, but it can be quite large, so do you impose a structure on the matrix, or do you just optimize it as a
No,
okay.
no, it's just randomly initialized, and sometimes you have an issue with some of the vectors will represent items that are very rare, and other vectors might be much more frequent, and so you have a conditioning issue for the optimizer. So in that case, using something like Adagrad or Adam might be better at optimizing this. But even just like SGD with momentum, most of the time it's good enough. And it's probably not a big problem to make errors on stuff that are very rare anyway. They are just identifiers. I don't know.
Okay, thanks.
Hey, thanks for the talk. Speaking of which, you said that by the end of your talk that we have to think about the ethical questions, such as filter bubbles and such. So how can you explain to the neural network that there's ethics that we need to configure, or filter bubbles that we need to avoid, considering that these rare events, these rare factors actually are present in the neural network as we learn it.
So what you can do first, if you want to tackle, for instance, fairness issues, is to label your test set by different population groups, and to compute the performance metrics on different population groups, and you can see whether or not some groups get very bad recommendations. That's a first step to do. That's quite easy to do. If you have some specific, like for instance, if you want to recommend job ads and you don't want to discriminate on gender, it's possible to train a neural net with what we call adversarial training. That basically you will have as an input all the user features and maybe the estimated gender. and as the output the quality of the recommendation, and also whether or not we could discriminate if the user was male or female. Actually, so male or female should not be part of the input. But then, when you train that network, is just that the loss will be tricked in a way that you will share a common representation for the two heads of your network, and you will basically, when you do backpropagation on the head of the gender, you flip the sign of the gradient, so that you penalize a representation that is able to capture whether or not a user is a male or a female. And so this way you will force your recommender systems to make predictions that don't depend on that specific feature. So it's a way to build internal representation that are fair in a way. But this is still an open area of research. But maybe I have the exact. Yeah, there is a paper called Censoring Representation with an Adversary. It was an iClear paper of 2016. Yeah, and also you can just compute recommendations for many users and flip the attributes of the user if they are explicit, and see whether or not you get a recommendation like manually to do a qualitative evaluation, basically.
Okay, thank you. Yeah, another question, quick question. Have you tried scaling these kind of algorithms? Scaling? Yeah.
So I think scaling, so there are two issues at train time and test time. Train time, I think it's not that a big issue because you use stochastic gradient descent, and so that's naturally a scalable algorithm. It's just very sequential, but it's out of core naturally. But at prediction time, what is very important is to get, if you have a very large number of users or items, items in that case, you need some kind of approximate nearest neighbors index to compute the similarities between items or a specific user representation and all the possible items in the catalog. This can be quite expensive, so you need some kind of